So yeah, we are also very happy to have Yonatan here on the expressivity of geometric MPNNs. Yeah, feel free to start. Or maybe can you like full screen the slides first?
Yes, it's not full screen.
Yes, now it is. Thank you.
Yes, thank you. Yeah, so I will talk about the expressive power of Sparse GNN. It will be more theoretical paper, but I think you will have fun. So first of all, it's not. Yes. So what is geometric graphs? It's graphs with position in R3. So in regular graphs, what we usually have is that we have adjacency and node features. But this doesn't capture many things like, for example, chemistry, dynamical, and physics. Physical systems that we have also position, and we want to be invariant also to group action on them. And unlike standard MPNNs, there is not a lot of theoretical work on geometric models. So we wanted to somehow close the gap and to understand better what is the expressive power of such models, because it's harder because of what we will see about the positions. Usually, expressiveness is discussed using separation and the ability to distinguish non-isomorphic graphs. So first of all, what is our setting? We have web adjacency that is in 0, 1 to the power of n by n. It means if there is edge or not. We assume that the graphs are undirected. And we also have positions. You can think like in physics, it's the actual position of the atom. And we denote by Gn all geometric graphs with at most n nodes. So what is our spatial group? Our group is the permutations, like always in GNNs, right? And also the rotations and the semi-direct product with translations. And how a group element PRT acts on a graph? Very, very simple. Like we know graph isomorphism on graphs, and we permute the nodes, rotate, and then translation. So this is how the group acts on this space. And we said that the graphs are symmetric, and we denote it by equivalent if there exists some group action that can take us from one graph to another. So it means that they are isomorphic also in the adjacency, but also in the positions that we can put them one on the other using rotation translation. And we say that the model is invariant, and this is usually what we care about in GNNs, is that if G1 is isomorphic to G2, then f of G1 will be equal to f of G2. And we kind of want also usually the opposite, right? But we will see that it's not always possible. Injectivity is not always something that we can obtain, not easily. And we now present two very, very popular variants of GNNs. The first one is very, very similar to standard MPNNs. So how it works? So first of all, we initialize with 0 all the node features. And then we do aggregation as we do usually. The current state, the state of the neighbors, but also the distance. So it's kind of MPNN with edge features. It's exactly the same. And after that, we do a readout in order to have a graph level prediction. And we assume that phi t is just a tuple mapping. Phi t and the readout are just multiset functions that they don't care about the order. They are invariant to the order. And for the analysis, we assume that phi t is injective, a standard injective mapping, and phi t and readout are injective multiset functions that they are not really injective, but they are injective up to some permutation on the input. And the second class is the equivariant GWL, that it works very similar. First, it initializes all the states with 0. And how we do the update, it's exactly the same, but we don't put the norm. We put the actual difference between the positions in order to, and we will see that it will will boost the expressivity of our models. And what are the assumptions? The assumptions are that phi should be tuple rotation equivariant. Phi is also rotation equivariant and multiset function because you don't want to care about the order. And F invariant is rotation invariant to get rid of the rotation. And then we apply a readout in order to get rid of the permutation. Because until this stage, we have equivariant also to permutation and rotation. So in order to get rid of it, we apply both functions. And also here we assume that phi is injective, and phi are injective as multiset function, and phi invariant is injective up to rotation, and readout is also injective multiset function. So we kind of need all these assumptions to characterize the expressivity. And what is known? It's known that by Ordan and Lee, that for generic, and we'll a little bit touch what is generic, for generic complete graphs that all edges appear, the invariant, the version that uses only the norm, is complete using one intermediate layer. And in addition, Joshi in 2023 proved that EGWL is strictly stronger than IGWL, but he didn't characterize which graphs each can separate. And our big question is which graphs IGWL and EGWL those models can separate. And in high level of our results, we show that EGWL can separate all connected graphs and only them. It's clear that not connected graphs, EGWL and any model that uses only edges cannot separate, right? Because this looks locally like this and this looks locally like this. And because there is no communication between these connected components, then their representation will be the same. So it's kind of a complete characterization of EGWL. And IGWL, we proved that they can separate only globally rigid graphs, which is a strict subset of connected graphs. And the intuition is, for example, these graphs. These graphs have the same distances, all is one unit, but they are not isomorphic, right? We cannot put them one on the other. But each IGWL that uses only the distances will say that they are the same, right? Because every node here and here have the same neighborhood. And this is an example of globally rigid graphs, and we also show that IGWL can separate those graphs. So what it means that we say generic, when we say generic, it means that they belong to some set that have a full Lebesgue measure. So it means that the points that we don't separate or we are wrong on them, they have a zero measure. It's kind of some assumption with the issue. And there are many generic assumptions in different papers. Yes, so now we define what is globally rigid because I didn't define it well. So globally rigid captures the problem of the IGWL. Because globally rigid graphs, they are graphs that if we know the distances along the edges, we can uniquely determine what are the distances along all tuples. So how we define it mathematically? Mathematically, we define it that if we have other y that agrees on all edges with x, then they agree on all tuples. And here the IGWL fails, right? Because if the graph is not globally rigid, then we have other tuples that they agree on the edges, but they don't agree on the tuples, and he cannot see it. So this is kind of intuition why IGWL fails. An example of globally rigid graphs are complete graphs. And this is connected to what Ordan proved, and this explained because complete graphs are globally rigid, and we proved that IGWL can separate all globally rigid graphs. So that's why they can separate all complete graphs. So it's kind of generalizes his result. And before the results, we just define what is means that a GNN identifies a pair. F identifies a pair XY. If you give me a Y and B other position and graph, so that f of XA and equals to f of YB, then AX is isomorphic to BY. So it means that from the output of the model on XA, I can reconstruct XA up to some group action. And we say that the model can identify specific combinatorial groups if it identifies A and X for any generic X. Right? So our first result, BA, a non-globally rigid graph, like for example, this graph is not globally rigid because we can see that we have all the distances are one, but we cannot define what are the distances along tuples, right? Because we cannot reconstruct the distance between this and this, for example. So those graphs, IGWL can't identify, not matter how many layers you take and how many features you take. But on the other hand, if A is globally rigid, we know that the graph is globally rigid, then IGWL with one layer can identify it. So this kind of makes sense, right? That the distances along edges is not enough. You need also the features, the actual positions, right? So this is what we will see in next slide. Yeah, so be a non-connected graph. Then, of course, EGWL can't identify it. This is the pair A. And it's clear that any geometric model that uses only direct edges cannot identify them. But on the other hand, if A is thus connected, then EGWL with D+1 layers can identify it. So it's kind of very, very cool that we get a full characterization of all graphs that those models can identify under the generic assumption. So this is kind of some issue. And so next we want to understand, like we know that, for example, in the WL world and the MPNNs, we want an MPNN that achieve the expressivity of WL, right? So other papers also from our lab, from Tal Amir and Nadav Dim, they presented how to build those injective multi-state aggregation functions. So actually building IGWL is not very difficult and it's possible. So achieving this expressivity is possible. The main problem is the equivalent GWL, and the problem is the aggregation there that is also injective, but also should be equivariant to rotations. So achieving both, and we also prove the reduction, it will probably very, very hard. It will be very expensive. So what we did is we constructed an aggregation that is injective on a generic point set. So it's not always injective, but it's injective most of the time. And this is enough for our theoretical results. And we call our model EGNet. And then we wanted to test our models on many benchmarks, but I present two. The first is K-chains. The K-chains is from a Joshi paper. I think he is the first to present it. It's kind of checking over squashing in GNets, that you have those graphs. Those graphs are not isomorphic, right? We cannot put them one on the other or rotate them in order to be like that. And each model, each equivalent model needs at least k over 2 plus 1 layers in order that the middle will have information from this and from this and from this and from this. So it's kind of requiring the problem radius to be high, right? And also no IGWL can separate them because all the distances here are 1, right? So we wanted to check all the models, what happens for k equals 12. In this case, each EGWL needs at least 7 layers. And let's see the results. And as we can see, we are the only one that succeeds with the minimal amount of layers, and also other models struggle to succeed. It may show that also these models suffer from oversquashing like ordinary MPNets. Those graphs, those models are not really EGWL because they use the complete graph. They don't use the underlying graph. And as we can see, all the invariant models succeed with 50%. That's because all the distances are one and they cannot separate them. So it's cool that we have success in kind of synthetic benchmark, and we show also for a real world benchmark that we show improvement in most of the benchmarks and also a high improvement. And it's kind of shows that our model that has also theoretical guarantees is good also in practice. And I think that's all, and my time is over, right? So thank you.
Thank you, Yonatan. I think we can stop the recording now.